It's my pleasure to welcome Dan Lustig. So Dan is a senior research scientist at NVIDIA, and he's been working on lots of fun things recently. Memory consistency models, I think maybe I know him best for that work, but also virtual memory and GPU systems. So request that everyone stay muted, as Mike mentioned, but also please feel free to ask questions on the Zoom chat anytime, and I will be taking those questions, consolidating them, and at the end of the presentation, we'll have a Q&A session with Dan. Great. Now with that, Dan, you can take it away.
All right. Thank you, Trevor, for the great introduction. Thanks, everyone, for having me. I'm happy to be here. So my name is Dan Lustig. As you said, I work for NVIDIA, and today I want to talk about memory systems and what we mean when we say that a memory system is programmable, and how we're going to incorporate forward-looking and emerging memory technologies, things like non-volatile memory, into these memory hierarchies that we're building, and how we make sure that those also stay programmable. There we go. So first of all, let's set kind of the big picture here, right? We're trying to build big systems, large systems, scale up to solve the really big problems that we're all trying to tackle today, right? And there's a number of high-level goals that I'll start with for systems like this. So first of all, right, we want them to be fast, high performance, right? There's a whole conference dedicated to performance analysis, so I'll assume we're all on board with that. But as a big counterbalance to making things high performance is making sure that they stay programmable. Generally, there's a bit of a trade-off there, right? The faster you want to make something, the more optimizations and new features that you put into something, the harder it is to actually program that or to get the efficiency that you're looking for out of it, right? And so pretty often you get a lot of systems that will have maybe very high peak throughput, peak performance, but if it's hard to actually achieve that performance, or you can't build an effective compiler for that system, that type of thing, then you don't actually get anywhere near that peak performance. And that's obviously not a good situation. It happens a lot, right? It's the difference between something that looks good on paper and something that looks good in the real world is being able to actually achieve that performance that you're looking for. So programmability is a really important characteristic of these large systems that we're trying to build, even though it's a little bit harder to quantify, or a lot harder to quantify than performance. And of course, everything has to work correctly, right? It's maybe not the most glamorous job in everybody's eyes, but it's a super important component of making things actually go from either research ideas or development ideas into production and into the wild. It has to work correctly. It's a growing portion of the overall cost of shipping a product. Often it's larger than the cost to actually design these things in the first place. So today I want to talk, focus kind of on the last two bullets here, programmability and verification, particularly from the perspective of the memory system. Because communication through memory is the foundation for these systems that we build, right? For lots of programming languages, for lots of systems at the hardware level. Shared memory is how these how all these different threads in the system communicate with each other, right? They issue loads and stores to a certain memory location, and other threads, other cores in the system read that same memory location, and that's how things communicate. And right, the set of rules defining how that communication happens and what it means to have correctness in this world is the memory consistency model. It defines the values that loads can return from memory given all the loads and stores that all the threads have been doing and what synchronization operations you've been performing. Right, so these things can start off pretty simple, and everyone learns kind of some version of this in classes. There's a lot more to it than what you learn in classes and from textbooks, though. So I want to spend some of the talk diving into what this stuff looks like in practice. Right, so the first thing you learn for these memory models is that weak memory models in particular can reorder certain memory accesses in order to get better performance, right? For example, I have a load and a store being issued here. The store got issued first from the thread on the way to memory, but for whatever reason, the microarchitecture decided it would be advantageous to reorder the load ahead of the store, right? And once you start reordering things like this, it gets a little bit harder to reason about because things are happening in orders that are different than the programmer was expecting originally. So that's where we get this programmability versus performance trade-off. And I get it. I know weak memory is not everybody's favorite topic. I happen to think it's a lot of fun, but I know it's very confusing and not a lot of people are super excited about the topic. So I want to make sure as I'm talking about memory consistency through the rest of the talk, I'm going to try to keep it accessible. I want to give kind of the big overall picture of how these things are deployed rather than diving too far into details here. But if you do have questions, like Trevor said, please put them in the chat. I'm planning to leave time at the end to answer questions. Okay, so what I said so far was kind of the simple picture of this. And in practice, and particularly for the type of system I showed in the first slide, it can get very complicated very fast. Right, the types of systems we're building at NVIDIA, for example, might look like this, with 4 GPUs, 8 GPUs in a single system. Each of these things has hundreds of thousands of threads all resident at the same time, right? And we have this kind of point-to-point connected thing that we call a memory system overall. These threads on all these GPUs have access to all of the other GPUs' memory as well as their own, right? So we have this single shared address space across this whole giant system. And we have to make sense of this somehow, right? It's not that we do this weak memory stuff just because we think it's fun or because, you know, we like formalisms or we like confusing people. It's not any of that. It's because these are the types of systems that we want to build and we are building. And so we have to find a way to wrap our heads around this somehow or other because we need people to be able to program the systems that we're building, right? So we have to figure out what it takes to make sense of all of this. So that's what motivates us digging deeper and deeper into this world of weak memory models. So today I want to talk about, as I said, what it looks like on the ground. So my experience is kind of seeing this from a couple different angles, both from the industry side and from the academic side. So I've done a bunch of academic research. The Czech suite is, I guess, what we've had a bunch of papers for in collaboration with Princeton, looking at things from the microarchitecture perspective. On the industry perspective, I'm one of the people responsible for developing the NVIDIA GPU memory model. And I also led the group that shared the RISC-V RVWMO weak memory model. So I've kind of come at this from a number of different angles, right? The very weak memory model of the GPU, the somewhere in the middle memory model of the RISC-V CPUs, and then academic perspective. And so that's what I want to talk about today, is not so much the what of memory models, but the how and the why of how we work with these things in practice. Because like I was saying earlier, like it or not, weak memory ordering is here to stay. It's not something we're going to get rid of, certainly in the GPU world. I'm pretty sure the CPUs that have it today are going to stick with it because there's a lot of advantages of it in spite of the complexity. And a recurring theme of what I'm going to talk about today is we have these tools and formalisms and techniques that we've built up over the past, say, 10, 15 years or so, which actually make this stuff, believe it or not, clearer than it's ever been before. And a lot of these techniques aren't really taught yet in textbooks. They're too new to have really propagated out to everybody. So that's I think the message that I want people to take away from this talk by the time we're done is that we're actually getting much better than we have been in the past about making sense of all of this, understanding all of this, and being able to use it productively and use it to our benefit rather than just sitting around being confused by it. And then towards the end, I'll talk a little bit about what all of this means for emerging memory technologies like non-volatile memory, right? Because these things are trending towards even weaker memory ordering than what we have today for normal memory. So if you think you're confused about weak memory ordering, and if it's already confusing, then we have to figure out what to do to make sure we have a handle on non-volatile memory and these other things before it starts getting even more out of hand. And I think we can do it. So I'll pass along also this quote from my colleague Olivier Giroux at NVIDIA, who also works on the NVIDIA memory model and the C++ memory model. Machines have taken over from the philosophers, right? We don't have to trust human expertise. We don't have to trust, we don't have to sit here and think about these things till our brains hurt anymore. We want to hand the to a small group of experts, say. So that's the plan for the talk. Okay, first of all, weak memory ordering. Why in the world do we have so much complexity here? What is the point of that? Why do we deal with this even though it gives a lot of people a giant headache? All right, so as we kind of hinted at earlier already, I think the first motivation and what's often taught, I think, is the primary motivation for these things is performance, right? The more relaxations you put into your memory model, the more optimizations you can put in, and therefore the more performance you get, or at least that's the principle, and people argue about exactly how much performance you can get. But at the end of the day, certainly that is one of the big motivations for doing these weak memory models. If there wasn't a benefit to all the optimizations, we probably wouldn't bother. But that's just one of the motivations for this. There's others that are equally important. So number two, for example, preserving architectural design space is something that's often very much underestimated, particularly in papers. And so what I mean by that is if we have a weak memory model that leaves more room for architects, micro-architects to do more optimizations, make more tweaks, either in current generations or reserving the right to make these changes in future generations, or not committing to do things a certain way for the current generation, then being stuck with that for future generations for decades to come, right? Often that's the type of timeline that we're thinking about in industry. It's not just building one product, but we want to have forward and backward compatibility across years, decades worth of products in the same family, right? So this notion of being able to preserve architectural design space by building a weak memory model that gives us permission to do these optimizations in either current generations or future generations, or to change our minds as we go, is super important. It's an underappreciated benefit of these weak memory models. And lastly, some of the complexity just comes in when we start doing kind of the modern approach to weak memory, which is filling in all the details needed to do formal verification of these things, filling in a complete, precise specification, and sometimes even building multiple different specifications for the same model and trying to make sure that they match each other. And sometimes, you know, this leads us to figuring out corner cases that no human has ever thought of before, but it's a bit of a gray area in the original spec, and we have to fill in a rule that clarifies that corner case. And so complexity creeps in for all of these different reasons. So let me dive a little bit into this formal verification idea to explain what I'm talking about. So first of all, performance, right? We hinted at this earlier already, but to give a little bit of an analogy here for how this actually gives us better performance, right? If we have a base case where everything is in order, going from each thread to the memory, everyone's stuck in traffic, all these memory accesses are stuck in traffic behind all the cars, all the memory accesses in front of them, then everything is going to be slow, right? So we say, what can we do to speed things up? What can we do to get better performance for the most important memory accesses that we want to issue? And so, for example, probably the most popular relaxation is to make the observation that loads are higher priority than stores. Loads are something that I need data for now, while stores are something I'm writing to memory so that I can use later. So loads are more important. I'm going to let the loads go into this express lane. I'm going to let the loads bypass the stores. And by doing so, they can sail right ahead. They can get where they're going faster, and therefore I get better overall performance. Right? And if we can do this in the right way, like in this particular example, we can do it in a way that maintains programmability. As it turns out, this particular optimization is fully compatible with what's called release consistency for free, meaning most synchronization operations just work. You don't have to change your code at all. There's a few corner cases where you have to change things, but overall, this type of trade-off is a clear win, right? You get better performance, you don't sacrifice programmability, everything is good. Where the challenges come in are where we keep adding more optimizations, more relaxations, and then we have to figure out what the rules are so we can properly define the architecture specs so that programmers know how to use it. Right, so performance, like I said, is just one piece of the puzzle. The big picture goal in modern approaches to memory models is really more like a puzzle. You don't get the complete picture until you find a way to fit all these different puzzle pieces together. So we have models at the software layer, we have models at the architecture layer, we have models at the microarchitecture layer, we might have even lower level models like RTL, we might have higher level frameworks or algorithms built on top of this. And the goal is to make sure that all these things actually interlock with each other exactly and precisely, right? It's like a jigsaw puzzle. You can't just force pieces into place that don't actually match up and line up with each other, right? You have to put everything in the right place so that everything lines up as it's supposed to, right? So this has actually been a major focus of the past 10, 15 years or so of memory model research, has not been building memory models in isolation. That's kind of what a lot of people, I think, sometimes think of when they think of memory models, people sitting around and just coming up with rules and, you know, whatever seems best is what we're going to do. It's not how that's done anymore. Today, we want to make sure explicitly that all these things fit together. And we do so not just with ad hoc analysis, but rigorous formal verification to make sure that we're actually covering all of our bases as we do this. Right. So, for example, the biggest concrete artifact for this type of analysis is what we call compiler mappings. And this is going to be our notion of programmability made concrete. As I said before, programmability is a hard thing to quantify. And so this isn't putting a number on it per se, but it's putting an actual concrete notion on it. Programmability doesn't have to be something we just kind of argue about vaguely or qualitatively, but now we get a nice rigorous definition of what it means for something to be programmable. So what does that look like? So what it means is when we take any arbitrary, say C++ programmer, pick your favorite high-level programming language, we have to figure out in the compiler how to translate that into assembly, right? That's what compilers do. From the memory model perspective, what that means is for a given type of synchronizing memory access, or call it atomic memory access in C++ lingo, we have to figure out what type of synchronization to put on that memory operation or around that memory operation, things like memory fences or memory barriers, for example. So in this example I'm showing here, this sequentially consistent atomic load is being translated into a load with a fence before it and a fence after it, and that particular set of fences, RW, RW, and RRW. And the way that works is not, it's actually a big misconception, I think, sometimes, is compilers aren't guessing to figure out what fences to put in there. They're not doing some kind of magic analysis as they look through the code, or they're not using heuristics to figure this out. These things in practice are all fixed recipes that people have determined in advance, right? So the compiler doesn't really have any sense of what memory order sequential consistency means. It's just looking these things up in a table, like the table I'm showing on the right here, that, oh, I have a list of all the different types of synchronizing memory access I can do. For each of those, I have a table that tells me exactly what fences to put in, and it doesn't say anything about why or how we got there. That was determined in advance by researchers that were doing the analysis offline to come up with that table and verified using formal proofs, right? So this type of thing, this artifact here is really one of the major goals and has been one of the major focuses of research for memory model researchers, coming up with this in order to prove that our architecture level memory model is compatible with the higher level language memory model, right? So this is, when we start doing stuff like this, we start using formal proofs to make sure that we got it right. We didn't miss any corner cases. This is why we start seeing all this kind of mathematical notation and complexity and pedantry, you might even call it, starting to creep into the way we specify these things, right? If you look at the, say, the C++ spec or the RISC-V memory model spec, or whichever spec you look at, they're full of all kinds of obscure terminology and wording that's probably pretty hard to understand if you're not familiar with it. But the reason all of that is there is because that's the type of language it ultimately takes to produce these tables, these compiler mappings, and make sure that they actually work the way we intend for any program that someone wants to write. Right, so this is what we mean by programmability in modern terms. And so as we were developing the memory models for RISC-V and for NVIDIA, this is what we had to do, is build tables just like this, and it's what every architecture has to do for itself, right? Every architecture has its own unique set of quirks for what types of fences that it has, what types of synchronization operations that it has, and so on. So I'm not going to dive too much deeper into how this works, because it gets deep into, you know, proofs and obscure notation of the kind I was just describing, but I wanted to set the stage, right? Programmability, it means this. And so, as I said, we build these proofs. They're not just proofs written by hand, but generally we use a automated theorem prover to make sure that we got it right. As I had that quote earlier, the machines are taking over for the philosophers, right? We trust the computers to verify this stuff because we don't trust ourselves. Even experts in the field don't trust themselves anymore to get this right. Right, so we build this proof that any arbitrary program you compile into a binary for your targeted architecture, any execution of that binary has to be an execution that was legal according to the original spec. And we can do this in a symbolic way so that it applies to any arbitrary program. And right, that's the level of standard that we're talking about these days, is full formalism. It's no longer enough to just kind of wing it, hope for the best, or just write some rules and hope that everything is covered. This is what's considered the state of the art for language specs, for architecture specs in the modern world. Right, and so as I said, all the formalism you see goes into building proofs like this. So what do we take away from this? I know that's diving kind of deep and doing a whirlwind tour of what it means to talk about programmability these days, but the takeaway is really that they're having these open-ended qualitative arguments about programmability, or how difficult it is to use a programming model or a memory model, are really obsolete. That's not the way things are done anymore, because we don't have to. We have a better approach, which is to actually just formally verify something. If you can say, I have my algorithm, I verified that it works at the software level, I verified that it works at the architecture level, I verified that it works at the microarchitecture level, then you have everything you need, right? You have your algorithm, you know, it runs correctly, and you can get the higher level, or the higher performance that you were looking for by going to these weak memory models. And so that's why we keep pushing aggressively on these formalisms, is not because it's confusing, not because we think it's fun, but because it solves a real problem that we have, which is we want to get these weak memory models that let us build these architectures that we want, and we want to be able to verify that our software actually works properly. So that's setting the stage for how memory models work overall these days. From here, I want to shift into kind of a retrospective on the NVIDIA GPU memory model. I joined NVIDIA about halfway through the process of developing the NVIDIA memory model, when kind of the basics were in place, but we were still proving out some of the details. So I want to talk a little bit about that experience. So first of all, GPU memory model at a super high level, it's a very, very relaxed memory model. Everything you have seen in classes about how memory models work, everything you might have heard about for complexity, we have pretty much all of it in our memory model. And we embrace that, right? It's probably, I know it's not easy for people to always wrap their heads around, but right, we have embraced it. We have doubled down on this notion of using weak memory to our advantage, right? So we have everything that's weak about memory models, but we also add complex notions that CPUs don't even have, things like scopes, where we, because the memory here is so non-uniform that you have an order of magnitude more bandwidth and lower latency to your local memory on your local GPU than you do to remote GPUs, for example. We put in this notion that you can explicitly specify which threads you're synchronizing with. We call that scope, right? So you can explicitly synchronize with threads in your same SN that's streaming multiprocessor, just the notion of core on the GPU. You can synchronize with other threads on the same GPU, or you can synchronize with threads on the whole system. And each of those has progressively larger and larger cost, right? So again, we recognize that it's complex, but this is what it takes to ship a big system like this these days. And so, as I said, when I came in, one of my first jobs, and my job still somewhat to this day, is reasoning about the memory model for big systems like this, trying to figure out how to make sense of this, make sure it works, make sure all the optimizations we're putting in underneath all of these cartoon blocks, making sure that those actually all work properly. And like everybody else who's tried this, we got it wrong at first. If you look back at history, there's papers showing things that we got wrong, and some of our early specs internally at least were wrong. It took us a number of different iterations to get this right. So it's not like it's easy for us. In fact, it's no easier for us. It's probably harder for us than others because of all the complexity. But that didn't deter us. It just motivated us to go fix it and go get it right the next time, right? So let's talk about how that process went. But before I do that, I want to quickly mention one thing, given this background I just talked about. So one brief aside, which I like to call the biggest contradiction of my job, which is seeing with my industry hat on, or I should more precisely say my NVIDIA hat on, that we're doubling down and embracing this notion of weak memory. But when I have my academia hat on, when I'm reading papers, reviewing papers, I see a lot of papers that are proposing things like what I'll call super coherence, which is a term I made up just for the sake of example here. No, like the movies say, no, any resemblance to real papers is unintentional, right? So, but I see a lot of papers doing this type of thing, that we propose some mechanism that provides stricter GPU memory ordering with just 5 to 10% performance degradation, whatever it is, and right, say no to weak memory models. And so my reaction to this is, it's weird, because on one hand, we're seeing like I said, industry is embracing weak memory models, and a lot of papers keep embracing stricter memory models. And it's this kind of weird trade-off that I'm still trying to make sense of, living in both worlds, given that I'm in industry research and kind of splitting the difference there. So I just want to comment quickly on how I think about this today, right? So these papers certainly have academic value. I don't want to say that people shouldn't do this type of research, because it's certainly interesting and informative to know what types of things we can build. But in practice, GPUs basically have no path to adopting stricter memory ordering anytime soon. Right, we're embracing this weak memory model for all the reasons I talked about earlier: performance, architectural flexibility, right? Well, yeah, performance matters, design space matters, language compatibility is what really matters. As long as we can prove we can program these things with, in our case, C++ or CUDA, that's what we're really after. So simplicity is a nice thing to have when all else is equal. But at the end of the day, relaxed memory models are something we actually embrace. We're happy with, we like the way we're going, we like the way things are going. And so it's unlikely that GPUs are going to adopt stricter memory, and we're certainly not going to do it if there's a performance degradation attached to it. So just a quick aside. But okay, back to the history of the GPU memory model. So we talked about proofs earlier and doing rigorous formal verification, but sometimes in practice, even that is not enough. It's happened more than once that proofs, after being studied, it turns out there's maybe some assumption they made in the very beginning that was not quite correct. And once you realize that that bad assumption was made and you take it out, the whole proof starts crumbling down, because everything was relying on that in ways that maybe didn't even anticipate. So I'm going to start this section with this quote from Knuth: "Beware of bugs in the above code. I've only proved it correct, not tried it." Meaning, proofs are great. We should do the proofs. They're super useful. But we also want to do this empirical testing to make sure that we haven't missed something. Don't just trust the proofs. Use everything we can, all the techniques we can, throw them all at the problem, and see if any of the above catch bugs. So what is a litmus test from the memory model perspective? It's generally small program meant to test memory behavior, like looking something like this, right? You can write any type of program you want. Programs generally are more than 7 lines, 8 lines, whatever this is, 6 lines of code. But these litmus tests really try to extract out the basic patterns that represent higher level synchronization in larger programs, right? So you might have a producer thread and a consumer thread, and the producer thread might write some data and then do some synchronization by storing, doing a release operation on a flag, and the consumer thread then has a spin loop waiting to see the updated value of the flag, and then checks that the data has actually been communicated properly, right? So without worrying about the details too much, it's really, in this case, building up a synchronization pattern between the store of data and the producer, and the load of data and the consumer, making sure things get communicated properly, right? So that's just one simple litmus test, right? We built up suites of these things over the years, and originally these came from just human brain power, plus some tools. We just generated some random tests, but really the most important test came from humans sitting around thinking about it, figuring out what types of patterns can we extract from higher level programs? What are the most interesting patterns, or what are the patterns representing, the corner cases that we can think about by staring at the rules in the model? And so we started with this one that we saw on the previous slide, and then we added some more. This is one that shows up in x86, and then we showed up in this other one. It's, oh, this is another corner case, and oh, now we have 3 threads, and it gets trickier. And we keep doing this. We keep sitting around thinking about them, and over time, like I said, we built up a suite of what became a standard suite of litmus tests. That there's actually a lot of commonality, as it turns out, fortunately, across different architectures and different languages. And while the details differ for each case, it's nice to have that common suite, so we have kind of a common language we can use when talking about different memory models. And sometimes, it gets complicated enough that even experts have headaches from thinking about these things. But if we're looking to do testing, because we don't want to just trust proofs and not actually test, right? We want to do these tests, we want to run them on hardware, make sure the hardware is working correctly, right? So we need to have a good test suite for testing our things. So NVIDIA was doing the same thing, right? We saw what everyone else was doing. We saw that this standard litmus test suite was kind of built up over time for other architectures, and we said, we're building our memory model. We want to do the same thing. So let's try to just generate all the tests that would apply to our complex memory model, and we'll use that as our test suite for empirical testing of the GPU. So we expected, the same kinds of tests to come out, and what we got, as my colleague Olivier so eloquently put it, was way more tests than we could possibly handle, right? We have so many parameters, so many degrees of freedom in our memory model that it's just out of control. It was just way impractical to deal with any of that. So we needed to find a better way to come up with a set of actually useful tests and kind of prune out the ones that were less interesting. And so that was an ISPASS paper we had a few years ago, was basically training a SAT solver to give us only what we consider to be interesting tests, the most interesting test, which is basically excluding tests which were over-constrained because they have extra synchronization more than is needed, or excluding tests which were under-constrained because they didn't have enough synchronization and therefore weren't actually testing anything interesting. There were plenty of test cases that were just redundant because it was an existing pattern with just, an extra instruction thrown in on the side for no good reason, or the same test but switching address names around or variable names around, right? There was a lot of symmetry and a lot of redundancy that we could prune out. And so, generating tests like that, which were actually constrained and tightly bound to our particular model and all of the parameters we actually care about, was actually an important step for us to be able to do effective testing on the GPU empirically. So the details of that were in that ISPASS paper there. But what's maybe more interesting coming out of this is once we did this, once we had a reasonable set of tests, we actually started noticing that a few of them failed right? They weren't actually working properly. And so we got nervous yet again that, oh no, our memory model is broken still. We're following all the rules. We're doing all these formalisms. We're trying to follow the state of the art, but we still have these problems that are coming up. And I'm showing one here on the left. It's 3 threads. It's this bizarre, obscure combination of synchronization operations that mean absolutely nothing to anybody, right? This is not a program a human would ever write. It's not a program that a human, even an expert in memory models, would write. It was not one of the tests in the existing suite, right? This is just something that came out of our deliberate approach to building tests that are tightly constrained to our memory model. We said, so this is a test that came out. It failed. That's essentially, or more precisely, C++ requires one of these 3 assertions scattered throughout this test to fail. But when we compile this onto the GPU using the compiler mappings we talked about in part 1 of the talk, and we execute it on the GPU, we are not required to have one of the assertions fails. So we have this weird mismatch, and it's completely unexpected. And so again, we started getting really nervous, and we weren't sure what to do about it. But then we looked a little bit deeper, and we said, wait a minute, this same issue that we're facing is actually true for other architectures that have weak memory. It's true for ARM, or at least older versions of ARM. It's true for IBM. Something weird is happening here. So we got nervous about this, but we started checking with others, and it turns out that some of my collaborators at Princeton were about to stumble on this. Some people in Germany, unrelated to us entirely, were starting to figure this out, that there was actually a bug in the way that things are being done kind of all over the place, right? So even with all these proofs and all this research going in, it's still possible to get things wrong. And so, right, that's why it's nice to have these tests that confirm that we're actually getting it right in the way that we think we're getting it right. So what did we do about this? Well, what went back and forth. There's a bunch of discussion on memory model mailing lists and such, to try to figure out what to do about it. And ultimately, the bug was resolved by refining the C++ spec. The original memory model came in with C++ 11. That's 2011. This happened 2016 timeframe, I think it was. And so there were papers that came out in around 2017 to try to fix this. Essentially, the idea was we have all this code that's out in the wild. We have compilers that are out in the wild. The compilers seem to be working for pretty much every real world program anyone's ever thought of. The type of program that fails is this type of obscure, bizarre program shown on the left here. It's not something we care about. So it's not something we care about in practice, I should say. So the way they decided to handle this was by refining the C++ spec, meaning adding even more complexity to it to resolve the subtle corner cases that came up when mixing and matching all kinds of obscure synchronization patterns with each other. And so at the end of the day, we were able to, save our own compiler, and we were able to collectively save IBM's and ARM's compiler. Everyone was able to, rescue all their products, which is great. No one wants to have some issue that, involves breaking code retroactively. So everything was good, and we can now put a gold medal on our machine friend here, who is able to come up with these tests that are actually useful, right? So takeaway from this section here is weak memory has been tamed, right? We have all these techniques we can now throw at the problem, right? Yes, it's complicated, but now we have this trust but verify approach, right? We have mathematical proofs that we use to verify the compiler mappings. We have empirical testing that's very targeted and is able to find useful test cases like this that maybe verify that the proofs didn't have any bad assumptions, or test all these weird corner cases that humans were never going to be able to come up with by themselves, because it's way too complicated even for experts. And so once we do this, once we have all this complexity under control, now NVIDIA and everyone else that wants to build aggressively weak memory models can build aggressive memory system optimizations in the real products, and we can actually do so with confidence, right? So the complexity, I know, can be scary, but once we get a handle on it, it's actually kind of liberating, because now when we put these new optimizations into the architecture, we don't have to sit there and worry about, well, I hope the programmer can make sense of this, or I hope we can build a compiler for this. No, we prove that it actually works, that we know what we're doing is correct, and therefore we can build it, with confidence. We know everything is going to be just fine. All right, so that's a very nice thing to have. And so a lot of the research I do these days is looking into new optimizations that push against this boundary that the weak memory model sets up for us very aggressively. HPCA paper last year, for example, about aggressive GPU cache coherence protocol that takes advantage, that very aggressively takes advantage of the optimizations permitted by the weak memory model. And another part of my job is just in general vetting new proposals that come up at NVIDIA for correctness, because there's always new optimization proposals coming up, and not a whole lot of people that really dive into the memory models. And so it's pretty common to just CC Dan on an email to see if we can make sense of this, right? So that's where I want to finish up in this last section here, is figuring out what we do about new proposals that come up. What else has weak memory ordering, either at the microarchitecture level or even exposed at the architecture level? And what do we do about all these new features that are coming up? How do we handle them? And hopefully I'm doing well on time. I'll try to speed up a little bit. So we have other forms of memory here, right? We speak a lot about the CPU cores, the data caches, the DRAM. We think of that as a memory system, but really there's a whole lot more to it, right? In real systems, there's persistent memory that we're now attaching to everything in various ways, which besides adding new functionality like keeping state after losing power, right? The trend is also towards having that be even more weakly ordered than normal memory. We have things like TLBs and instruction caches, which are not generally kept coherent with the data caches. We have processing in and near memory that adds even more complexity, even more new features, and changes functionality in the memory system. And so we have to find ways to make sense of all of this as well. So memory models are expanding here, and all of these have similar problems, or are likely to have similar problems to the types of examples I just described if we actually start looking at them. So fortunately, people are starting to look at these things, persistency, memory ordering for persistent memory or non-volatile memory. People are looking at translation, address translation consistency. People are looking at instruction fetch consistency. I'll speed up a little bit and just point out one quick example that comes up, which is this paper here from last year shows that Chrome's WebAssembly JIT is relying on certain in-order instruction fetch behavior not currently specified by any of the major architectures, right? So people are already starting to create these optimizations that rely on aggressive weak memory ordering, but relying on implementation details for instruction caches and TLBs, and pretty soon they're going to be doing it for non-volatile memory. And so I want to encourage people to start thinking about adding all of these things into the same type of jigsaw puzzle framework that we built up for normal memory. That we have ways to do this. We have the formalisms, we have the proofs, we have the litmus tests. I think we should start doing all the same type of stuff for persistent memory and TLBs and instruction consistency. And so it's good to see that there's a little bit of work at least starting to go in this area. And very, very briefly, I'll mention again this check suite that I worked on with my colleagues at Princeton, which is verifying, extending this jigsaw puzzle verification down to the microarchitecture level, modeling things like complex pipelines and caches and cache coherence, TLBs, TLB shootdowns, everything that's going on at the microarchitecture level to try to rigorously verify that against the stack the same way we've been doing as a community for the software and the architecture levels. But unfortunately, I don't have much time to talk about that today. And side benefit, this has also shown some interesting results for modeling security properties like cache side channels, which Caroline Triple at Stanford has been looking at. Okay, so to wrap up, last slide here. The conclusion, the thing I want people to take away from this is that memory models, weak memory models can be confusing, yes, but we've conquered them. We now have the tools to be able to deal with them and to understand everything that's going on with them. We no longer have to have these open-ended programmability debates or difficulty debates. Nothing is floating around in isolation. All these things now are designed to fit together, where we can, to the point that we can get full formal verification of compatibility from top to bottom in the stack. And because persistent memory and instruction fetch TLBs are doing all these same things, or even getting even more aggressive, and people are starting to rely on the implementation details, we should get out ahead of this and verify that things are working properly using all the techniques that we've developed, because now we have the tools to do it right. We can rely on theorem provers and SAT solvers and so on to do all the heavy lifting, so that we don't have to rely on human ingenuity anymore. We now have the tools to do this right. And with that, I will finish up, and I'm happy to take questions.
Great. So thanks so much, Dan. So I'm going to clap for you for all that hard work. It's really tough to work and get feedback from an audience on a virtual conference. So we can just, I've done a little bit of clapping for you, but thanks so much for that overview of a huge amount of excellent work. And you're right, it's about, it seems to be about how difficult things are, right? And how you guys are working to clear things up, right? So we have some questions here. And I guess you sort of mentioned this at the end, right? With respect to verification of the memory models, right? And how things are changing for full system, right? You talked about lots of things, PIM and non-volatile memory and things like that. But the verification of models is one direction, right? And so the other is just understanding what the future of those memory models themselves will be, right? Because yes, we can now formally verify them, right? And that's really awesome. But doesn't that now give us permission to do a lot more, right? And push the envelope even more?
It does. Yeah, so I mean, NVIDIA's memory model, for example, where we have one that's solid now, doesn't mean we're done. We're still looking at even more optimizations that we can put in, and some of that's going to propagate up into the architecture memory model. I mean, with our Ampere generation, for example, we added asynchronous copies, which is even more relaxed than what normal memory is doing. And we're still looking at more stuff coming down the pipe, right? So I think people are definitely going to keep looking at more optimizations. If you look at like persistency, for example, people are talking about relaxed persistency, which means weaker than consistency. If you want to do something, if you want to make memory persist in the right order, you need extra synchronization beyond what the normal memory is going to require. And so I think there's a lot of temptation to keep putting things like that in for performance reasons. And I think, yeah, that's generally what motivates people to put them in, is because they found it to be advantageous in some way. But like I said, the counterbalance to that is making sure that programmers are actually going to be able to use that, which means making sure they can wrap their heads around it, making sure there's a valid exposure of that at the architecture level and at the software level, or put it in libraries or something. Right? There's different ways to expose different features, but somehow that type of stack has to be built up in order for people to actually do these things. So I hope people do keep aggressively looking into these things. So that's how we're going to move the field forward. But hopefully we have the tools and proofs and whatnot to back it up as we do that.
Right. One of the things that, is interesting, I find interesting here, is that, we've seen memory models compared now. So there's a recent micro paper that looked at the RISC-V weak memory model comparing it to TSO. But from what I remember, and I could be wrong, the performance differences weren't huge, right? And of course, this was on the CPU side, right, where the number of threads just does not approach the level of what you are demonstrating here. So is this really a GPU only issue? Or is this something that we also, because it seems from the recent paper, it just seems that the CPUs aren't getting as big of a benefit as you're describing, right?
Great question. Yeah, so well, I can speak from the experience of RISC-V, where that was actually one of the big debates that we had for more than a year was, should we strengthen the model to be TSO, more strictly ordered, or should we keep it where it was to start with and just fill in the details, which was the more weakly ordered model now called RVWMO. And yeah, it's hard to, well, sometimes it's hard to quantify these things. Sometimes it depends, right, a lot on the system you're building. There are definitely ways you can build stricter ordering microarchitectures that deliver good performance, right? I mean, x86 has pretty strict memory ordering and has been the kind of flagship high performance architecture for a long time now. Maybe things are changing now, but x86 has been dominating the server space for a while with strict ordering, right? So it's not the case that you can't build high performance machines with strict ordering, even on the CPU side. It's more that you have to put in a lot more features in your architecture to kind of cover up the reorderings that are happening underneath, right? You have to dive deeper into speculation, or there's maybe certain other optimizations you're forbidden from doing. So you have to be more aggressive in other ways to make up for that fact, right? So sometimes you can get that performance back by putting in those types of things, and you can get pretty close to where the relaxed memory models are. But then you're committed to doing that in every processor you build in order to maintain that performance. I think that's the kind of underestimated trade-off there is if you go with a strict memory model, you're committing yourself to always having to do all of those tricks in order to get that performance. Whereas if you have a relaxed memory model, you're welcome to put them in if you want to. You're welcome to not put them in if you want to, right? It's every optimizer or every implementer can make their own decision. I think particularly for RISC-V CPUs, that was one of the big factors in favor of keeping it weak, was that there's so many different vendors for RISC-V, whether it's industry or hobbyists or academics or startups. They're all over the place, and everyone wants to build the systems they want to. And so having fewer constraints requiring people to build all kinds of optimizations like that, super aggressive things in order to get performance, was just less appealing. So that's why we went with the weak memory model, and even for CPUs.
Interesting. So we had one question here, and we're a little bit over, so we're going to, this is probably one of the last questions, unless we have some more. But one other question here was talking about the memory consistency models and litmus tests from the perspective of the system with memory consistency, and now you can also look at it from a security perspective, right? And you mentioned like Caroline's work, right? And I guess maybe the question here is, are there a lot of parallels that can move over into the security domain? Is this something that architects should be looking into? And maybe another thing to think about is, are the tools that you have readily extendable to something like this?
Great question. Yeah, I think we all got a wake-up call a few years ago with Spectre and Meltdown, right? I think so. Everyone knows now that security is even more important than we all thought it was before, and everyone's paying a lot more attention to it these days. And I think as a community, I would say we're all collectively on the lookout for what it would take to build a formal security model in the same way that we build memory models or other parts of the architecture, right? That's one of the weird things about Spectre and Meltdown is technically the architecture spec wasn't violated. It's really more of a microarchitectural side channel, right? So you could argue that even Meltdown kind of sort of wasn't really a bug, depending on how you define bug, right? Yeah. You can have that debate, but really the way forward, I think, would be to try to come up with a formal spec of some kind that more rigorously, or whether formal or at least more rigorously defines what security properties we want and what it would take to get there. So yeah, like Caroline's work was a very interesting offshoot of the work we started at Princeton for memory models, which was, yeah, like I said, noticing that the same types of techniques we were building to model caches at the microarchitecture level for memory ordering purposes, you could use a lot of that same type of framework for security and trying to avoid side channels by modeling, occupancy in the cache or lack of occupancy in the cache. And yeah, she was able to actually do some pretty interesting stuff, turning those techniques into actual exploits, variants of the Spectre and Meltdown attacks. So I think there's a lot of interesting promise there, and I'm pretty curious to see where it goes. But I hope the techniques we're building give at least some examples and some foundation that security researchers will be able to build off of as they keep trying to achieve that goal of building that type of security model.
Well, thanks, Dan, for your great talk again. And unfortunately, we're out of time here, but even a few minutes over. But anyway, thanks for that. That was great, and for all of the background, and again for all the work, the topics, and congratulations on all of that. And keep up the good work. And I hope that we will be seeing some of your work in the coming years as new processors and GPUs are released. So thanks again for everything, Dan.
Yeah, thanks again for having me.